as usual. And yeah, welcome. It's another day. So in our previous lesson, we talked about alkanes, preparation of alkanes, from alkyne halides, from carboxylic acids, from alkenes and alkynes, and the video is there. As usual, you can always go back and watch the video and enjoy that science. Then we talked about the physical properties, if you remember, of alkanes, where we saw that low alkanes, they exist as gases, and high alkanes, they exist as solids. Then middle ones, from around carbon 4, carbon 9, they do exist as liquids at room temperature. And it all goes to the boiling points. Then we showed that we try to explain the trend in melting points among these alkanes vis-a-vis alcohols and carboxylic acids. Okay, where we saw that alkanes have the lowest boiling point, and the carboxylic acids and alcohols have higher boiling point. And the reason that we gave, they are the intermolecular forces of attraction, the van der Waals, and then the hydrogen bonding. And we really explained this, okay? And the video is there. You can always go back and refer to it. So let's talk about within alkanes themselves. And like we said, within alkanes, the boiling point generally increases with the increase in molecular weight. And you can clearly see that the low alkanes from C1 to something like C3, though some books say C4. So you can fact check. They are gases at room temperature. But the middle ones, for them they are liquids. Okay? Liquids. And from the higher ones, from C9 and above, now these ones they are solids. So what does this imply? It implies that this intermolecular forces of attraction holding these molecules together, they become stronger and stronger as you go, as the carbon chain increases. Why? It goes back to the van der Waals forces of attraction. Okay? That these molecules being non-polar, they are held together by the van der Waals forces of attraction. Okay? Van, this was a Dutch scientist. The Waals forces of attraction. Now there are these ones that do exist among non-polar substances. And so,
What are polar substances?
polar substances, they are those substances that have charges, that are charged. So they show dipole moment, where the positive attracts negative and negative attracts positive. So they have those forces of attraction. And the forces of attraction within polar molecules, they are hydrogen bonds. But now here with non-polar molecules, such as our alkanes, they do have the van der Waals forces of attraction, whose magnitude, whose strength increases with increase in molecular mass. What is the logic with molecular mass? You see, if you are just C4, your size, the molecules are generally small. They are generally small. But if the molecular weight increases, maybe to C9, H20, then the size increases. Okay? And so the bigger the size of your molecules, the stronger the attraction, the stronger the forces of attraction that will exist within the molecules. And the stronger the attraction, then the higher the boiling point. But in these ones where they have just small molecules, then the molecules will be farther apart from each other. And if the molecules are farther apart from each other, then they are weakly attracted to each other, and so form weak van der Waals forces of attraction, hence have generally low boiling and melting points. So if you clearly understand that, then it is a good explanation for the increase in melting point among alkanes themselves. So ethane, for instance, with molecular mass of 30, it boils at lower temperature than butane with molecular mass of 58. Okay? So increase in molecular weight increases the sizes of molecules, which correspondingly increases the magnitude of the van der Waals forces of attraction. And so if you increase the magnitude of the van der Waals forces of attraction, and what does that imply to you? You will require generally much heat to break those forces of attraction, and hence a higher melting or boiling point. However, now for branched compounds, okay, for branched compounds, for example, you may have this N, this is N-pentane.
Should I prefer the previous slide?
Okay, previous slide, it's okay, no worries. You're writing notes?
No.
Okay. Anything that I should explain on the previous slide?
I'm done.
Okay, that's good. That's good. So, however, with branching, for instance, let's compare these two. This is N-pentane, and I told you N means normal. N-pentane. With N-pentane, you can see 1, 2, 3, 4, 5. With molecular mass 72. And, Anita, can you name this for us? And please hurry up.
What?
You name this for us, this one. The IUPAC name of this.
It is 2-methyl propane.
Something small, missing.
2-dimethyl propane. Is it?
Something small, missing.
I don't know. What is missing?
I'll beat you up.
Propane.
So it
has a double bond?
No. Oh. You've missed just another 2. So it is.
Why is it supposed to be there?
So it is 2,2-dimethyl.
But teacher.
Yes.
If I try to remember, you gave us that thing some good time back.
Yes.
you gave us the name of that structure,
Yes,
for which you gave us 2-methylpropane,
I gave you.
and then
Mm,
2-methylpropane, and then you're coming here. You are saying 2,2-dimethyl, and where is the di coming from?
I gave you 2,2-dimethylpropane.
Teacher, no, you gave us 2-methylpropane.
Edwin, what did I give you?
He wasn't there. It was Nyando's team who attended that day.
Are you sure?
Yes.
As if he has never missed any lesson.
Eh, that day.
So
Just because I don't.
because the team is not around.
No, I'm not trying to lie. But
Anyway,
that's the fact.
I'll go through my videos, but what I'm quite sure of, I gave you this 2,2-dimethyl, or even if I gave you 2-methyl, maybe it was just a mistake.
And where
But
is the other two coming
but
from?
I'm quite sure I gave you 2,2-dimethyl propane. So you see, you have two methyl groups, this one and this one, and they are all attached on carbon number 2. So when you just say 2, it means it's 1. But because they are 2, then it's 2 and then another 2, and then you say dimethyl. It
Why is the di coming from?
Because they are 2. Di means 2. This one and this one.
I now what if they were three, which is impossible. Okay.
It is
It's like
possible. It's possible. It can be this CH3. Then see you have this one. You have this one.
on the same carbon.
On the same, no, it can't happen on the same carbon.
Teacher,
Yes.
so, you see, I thought that you've already written the two. Oh, my phone.
So if it's this, then it becomes 2,2,3 trimethyl 1,2,3,4 butane. So as simple as that. Okay.
Yes.
So nomenclature really should be part of you. We shall always study nomenclature, right from alkanes up to amines. We shall always study nomenclature. So it should really be part of you. So now, in 2,2-dimethyl propane and N-pentane, they all have the same molecular formula, molecular mass. Okay? You can see 72, 72. But surprisingly, this one boils at relatively high temperature than this. Think about it. N-pentane boils at high temperature. Actually, there's somebody who asked, I think it's Otim. He asked between this and then cyclopentane, which one is going to boil at a high temperature. So this is almost the same as this. Now in N-pentane, the molecules are stretched. Okay? They are stretched. But in branched, the molecules are just branched. So the stretched ones have relatively larger sizes than these branched ones with smaller sizes. And so what does that imply? Write what I explained. When the atoms are large in size, okay, it means these atoms are close to each other than when the atoms are small in size. And the closer the atoms, the stronger the van der Waals forces of attraction that are formed within these very atoms. And so if they form strong forces of attraction within themselves, then you will require relatively high temperature to break these forces of attraction, hence a higher boiling point than when the atoms are small in size. Is that okay? Yes. So let us see. So in 2,2-dimethylpropane, it boils at relatively lower temperature than N-pentane, yet both have the same molecular weight, as you can see. Okay? Why? In N-pentane or in 2,2-dimethylpropane, it is highly branched, as you can see, which gives it a spherical shape that reduces its size, and hence form weaker van der Waals forces of attraction. And therefore, those weak forces, they are relatively broken at lower temperature compared to N-pentane that will be stretched, hence form stronger van der Waals forces of attraction. While in normal pentane, N-pentane, being a straight chain molecule, it gives it an extended structure, which results into relatively stronger van der Waals forces of attraction, hence requiring too much energy to break. Is that really okay to all of us? Yes. So this is where I'm going to stop recording the video from, because there are videos now right from combustion of alkanes.
Charlie.
Because, oh, sorry.